Jeluri, Associate Professor of Physics, Institute of Aeronautical Engineering. Today I wish to tell about the question bank on lasers and fiber optics. So, in this first question, the first problem is find the relative population of the two states in a ruby laser that produces a light beam of wavelength 6943 angstroms at 300 degree Kelvin. So here in this problem, we have to find the relative population of the two states, which is in the ruby laser. So the laser, that is the light beam, have the wavelength 6943 angstroms, which is at the 300 degree Kelvin. So the given data is lambda, that is 6943 angstroms. So 693 angstroms. So if it is converted into meters, then 6943 into 10 power minus 10 meters. And then temperature. So temperature T is equals to 300 degree Kelvin. So we need to find the relative population of the two states. Relative population of the two states. So that is how we have to find the relative population of the two states. Suppose if in this problem we need to find the relative population of the two states. So let assume that E1 is the lower energy state and E2 is the excited energy state. So this is low energy state, that is ground state. Ground state, and this is excited state. So these are the two states in the ruby laser, and then here we need to find the relative population. So let the population in the lower energy state, that is ground state, is N1, and excited state population is N2. So N1 is so let N1 is the number of atoms in the number of atoms per unit volume in the ground state, and N2 is the number of atoms per unit volume in the excited state. So we need to find the relative population between these two states, relative population between these two states. So that is the population of the two states is N1 and N2, or the population of two states. Population of two states. So when we want a relative population, we have to take N2 by N1. N2 by N1. As here in the ruby laser, it is working under the optical. It works under the relative population of the two states is N2 by N1. So where here in this case of ruby laser, so ruby laser works by the mechanism of optical pumping. So optical pumping mechanism is used in the ruby laser. to make the ratio N2A is greater than N1. So in general case, N1 is greater than N2. So generally, the number of atoms per unit volume in the ground state is greater than the number of atoms per unit volume in the excited state. It is the general case. Generally, it is in the ratio of N1 is greater than N2. But in the pumping mechanism, so to make stimulated emissions, okay, so here there is a condition N2 is greater than N1. So to make N2 is greater than N1, so we use pumping mechanisms. So in that pumping mechanisms, one of the mechanism is optical pump. We have a chemical reaction method and elastic inelastic collisions, and then optical pumping, electric discharge, like that. We have different mechanisms to excite the atoms to higher energy state, so that this condition will be satisfied. So when the condition N2 is greater than N1 be happen, then we can get the laser light, that is stimulated emissions takes place. So to make N2 is greater than N1, we use optical pumping in the ruby laser. So N2 is greater than N1 here. So we need to find this N2 by N1 ratio of N2 and N1. So the population ratio N2 by N1 in the formula e power minus of E2 minus E1 by KT. So where N1 is the number of atoms per unit volume in the ground state, that is E1. N2 is the number of atoms per unit volume in the excited state, E2. So now E2 minus E1 is equals to H nu. So nu is nothing but C by lambda. So from the blanks, E2 minus E1 is equals to H nu. So that is the emitted photon. So when the atom jumps from excited state to ground state, it emits photon. So that photon radiation is H nu. So this photon radiation is equals to the energy difference between the two energy states, that is E2 minus E1. So E2 minus E1 is equal to H nu, where nu is C by lambda, so that H into C by lambda joules. So N1 by N2 is equals to exponential of substituting the values, that is E2 minus E1 by KT. So here we are using E2 minus E1 is equals to Hc by lambda joules. So that in this N2 by N1 is equals to e power minus of this E2 minus E1, that is Hc by lambda divided by KT. So N2 by N1 is equals to e power minus of E2 minus E1 by KT. So e power minus of Hc by lambda by KT. So we know that why Hc by lambda comes, that is E2 minus E1 is equals to Hc by lambda joules. So substitute now N2 by N1 becomes e power, that is exponential of minus Hc by lambda KT. So e power minus the value of H is So h is Planck's constant, that is 6.625 into 10 power minus 34 joule second. And the velocity of light, this is Planck's constant. And c is the velocity of light. So the velocity of light 3 into 10 power 8 meters per second. So minus of 6.625 into 10 power minus 34 into 3 into 10 power 8 divided by lambda. Lambda is given in the problem 6943 angstrom. So into 10 power minus 10 meters. So 6943 into 10 power minus 10 meters into K. K is the Boltzmann constant. So that is 1.38 into 10 power minus 23, and T is the 300 degree K. So the value is N2 by N1 is equal to N2 by N1 is equals to 6e power minus 69.3, that is equals to 8 into 10 power minus 30. This is the relative population of the two states in the ruby laser. So N2 by N1. So relative population of the two states is 8 into 10 power minus 30. Next problem, for a helium neon laser at 1 meter and 2 meter distances from the laser, the output beam spot diameters are 4 millimeters and 6 millimeter respectively. Calculate the divergence. So in the problem, we have to calculate the divergence, but the given data is distances. So distances from the laser output, distances from the laser. So the distance was, let assume, the given data is D1, the distance. So D1 is 1 meter and the second distance is 2 meters. So this is the distance of the helium neon laser from the source to the screen. That is, so this is the laser source. That is helium neon laser source, and here the screen is. Here the screen is. So the spot is here. So at 1 meter distance, that is the distance is calculated from source to the spot. Source to the spot D1. So this D1 is 1 meter. When the distance D1 is equals to 1 meter, the spot diameter, this spot diameter, let's suppose A1. So this A1 is equals to 4 millimeter. And then when the distance is increased, so that is D2. D2 is equals to 2 meter distance. Then this spot diameter A2 is equals to 6 millimeter. A2 is equals to 6 millimeter. A2 is equals to 6 millimeter. So the diameter will be calculated like this. Suppose this is the laser spot. So we have to calculate this diameter from here to here the point. So that's the diameters are for 1 meter of distance. A1 is the diameter is 4 millimeter. For 2 meters of distance, A2 is 6 millimeters. But we need to calculate the divergence. So we need to calculate the divergence. That is, if the distance of the source to screen is far away, then the diameter of the spot diameter will be changes. That is, it is decreased. The diameter will be decreased. So here we need to so the spot will be here when it is at 1 meter, 1 millimeter, so 1 meter of distance. Let's suppose. And if we take a 2 meter of distance, so this is the so here we need to, this is the laser spot. So this is the laser source and D1, D2 are the distances. So we need to calculate this divergence. We need to calculate this divergence theta. Calculate the divergence of this wing, laser light. So for that we use the laser divergence formula. So laser divergence formula, theta is equals to A2 minus A1 by 2 into D2 minus D1. So the given data, D1 is equals to 1 meter and D2 is equals to 2 meters. And the diameters are A1 is equals to 4 millimeters and A2 is equals to 6 millimeters. And need to calculate the divergence of laser theta. So laser divergence theta is equals to A2 minus A1 by 2 into D2 minus D1. So A2 is 6. So 6 meters, if we convert meter, 6 into 10 power minus 3 meters. Like for this same, A1 is equals to 4 into 10 power minus 3 meters. So 6 into 10 power minus 3 minus 4 into 10 power minus 3 divided by 2 into D2 is 2 meters minus D1 is 1. So it is equals to 6 minus 4 into 10 power minus 3 divided by 2 into 1. So 2 into 10 power minus 3 by 2. So it is 1 into 10 power minus 3 radians. So the laser divergence is in laser divergence theta is equals to 1 into 10 power minus 3 radians, or else theta is equals to 1 milliradians. So this is the laser divergence of this given problem. So the answer is theta laser divergence is equals to 1 milliradians. Next problem. A helium neon laser emits light at a wavelength of 632.8 nanometers and has an output power of 2.3 millihertz. How many photons are emitted in each minute by this laser when operated? So the given data is wavelength of the laser beam. So that is 632.8 nanometers. So when converted into meters, so it is 6328 into 10 power minus 10 meters. That is lambda is equals to 632.8 nanometers. So it is equals to 632.8 in 10 power minus 9 meters. So 632, when taking this out, 6328 into 10 power minus 10 meters. So this is the lambda given. And output power, so the output power P is equals to 2.3 milliwatts. So 2.3 into 10 power minus 3 joules. So we need to calculate the number of photons that are emitted per minute. So time also mentioned. So number of photons are emitted in each minute we need to calculate. So number of photons emitted per minute. This we need to calculate. So the formula is power output P is equals to NH nu. So in this we need to calculate number of photons. So from this formula N is equals to P by H nu. But nu frequency, nu is equals to C by lambda. We can take like this. Nu is equals to C by lambda. Then number of photons N is equals to P by H C by lambda. So that is P by H C by lambda. So this can be written as N is equals to P into lambda by Hc. So P lambda by Hc. So let's substitute in this expression. So N is equals to P lambda by Hc, where output power is 2.3 into 10 power minus 3. So where here it is mentioned per minute, so that into 60, then it becomes 12 per minute. And the lambda is 6328 into 10 power minus 10 divided by H is 6.626 or 65 into 10 power minus 34 into C is the velocity of light 3 into 10 power 8. So when calculating this we get 4.3949 into 10 power 17 photons per minute. Photons per minute. So, number of photons are emitted per each minute. Each minute is 4.3949 into 10 power 17 photons per minute. Next, solve the wavelength of emitted radiation from gallium arsenide, which has a band gap of 1.44 electron volts. So, given data is energy gap of gallium arsenide. Eg is equals to 1.44 electron volts. So, that is equals to 1 electron volts is equals to 1.6 into 10 power minus 90 joule. So converting into joules, so 1.44 into electron volts is 1.6 into 10 power minus 90 joule. So we need to calculate the wavelength lambda. So the relation between the wavelength and the energy gap is Eg. Energy gap Eg is equals to h nu. So that is equals to h into c by lambda. So Eg is equals to hc by lambda. But Eg has been given and we know the Planck's constant and the velocity of light, but we have to calculate the lambda. So for that, lambda is equals to hc by Eg. Eg is energy gap. Energy gap of a semiconductor. So as you know that a semiconductor, we have valency band and conduction band. So lower band is the valency band and excited, that is excited energy levels or being in the conduction band. So this is valency band and this is conduction band. So in the semiconductor, so the energy gap is minimum between conduction band and valency band. These are the energy levels in the conduction band and these are the energy levels in the valency band. So here in between valency band and conduction band, there is an energy gap. So here it has been given gallium arsenide semiconductor. The energy gap is 1.44 electron volts. For gallium arsenide, the energy gap Eg is 1.44 electron volts. But we need to calculate what is the wavelength. So for this semiconductor, we have to calculate the wavelength. As you know that semiconductor which is partially conducting material. Partially in the sense of at 0 degree Kelvin, it doesn't conducts the current. So it acts as a insulator. When it attains room temperature, then it conducts the current. So it acts as a conductor. So here the energy gap between a valency band and conduction band is 1.44 electron volts, but needed to calculate the wavelength. So the formula is lambda is equals to hc by Eg. So let's substitute the values of each. So h is 6.626 into 10 power minus 34 into velocity of light is 3 into 10 power 8 meters per second divided by 1.44 Eg. 1.44 into 1.6 into 10 power minus 90 joule. So when calculating this, we'll get 8633 into 10 power minus 10 meters. So here in the next problem, a semiconductor laser diode has a wavelength 1.55 micrometers. Estimate its energy gap in electron volts. So in the given problem, the data is wavelength. So the wavelength lambda is equals to 1.55 micrometers. So 1 micro is equals to 1.55 into 10 minus 6. So 1 micro is equals to 10 power minus 6. So we have to calculate the energy gap of a semiconductor. So energy gap of semiconductor Ag we need to calculate. So the same formula which we used in the previous problem, formula Eg is equals to Hc by lambda. So there we took lambda from this formula. So from this formula we took lambda to calculate. So here directly we have to calculate the energy gap. Eg is equals to Hc by lambda. So because lambda has been given. So let's substitute the value 6.626 into 10 power minus 34 joules into 3 into 10 power 8 divided by lambda is 1.55 into 10 power minus 6. So it is equals to 0.8 electron volts. This is in electron volts. So where 1 electron volt is equals to 1.6 into 10 power minus 90 joules. So when Joule wanted to calculating the electron volts, we have to divide this expression with this 1.6 into 10 power minus 90. So from this expression, we'll get the energy gap in joules. When this expression is divided with 1.6 into 10 power minus 19, then it will convert it into electron volts. So let's see. Eg is equals to 6.626 into 10 power minus 34 into 3 into 10 power 8 divided by 1.55 into 10 power minus 6 into 1.6 into 10 power minus 19 electron volts. So then we put the value 0.8 electron volts. So this is the answer. Next, a step index fiber has a numerical aperture of 0.16 and core refractive index of 1.45. Estimate acceptance angle of the fiber and refractive index of the cladding. So the given data is step index optical fiber has a numerical aperture. So numerical aperture NA, so 0.16. Core refractive index. Let the core refractive index is N1, so that is equals to 1.45. And then estimate acceptance angle. So we need to theta maximum or theta A or I maximum. So theta A is nothing but acceptance angle, theta A, or else in some other cases we may mention also I maximum. So the maximum acceptance angle, I maximum. Then also need to calculate the refractive index of the cladding. So refractive index of the cladding is N2. So let's calculate. We have to calculate the acceptance angle and also refractive index of the cladding. So first we'll see acceptance angle formula. So acceptance angle I maximum or theta A is equals to sine inverse of NA, sine inverse of numerical aperture. So numerical aperture is given. So sine inverse of 0.16. So acceptance angle I maximum is equals to 9.206. For the second, we need to calculate refractive index of cladding. That is N2. N2 is equals to root of N1 square minus NA square. How we got this expression? From the formula of NA. NA is equals to root of N1 square minus N2 square. So from this squaring both, so NA square is equals to root of N1 square minus N2 square. So that NA square is equals to N1 square minus N2 square. From this N2 square, so NA square minus N1 square is equals to minus N2 square. So N2 square is equals to N1 square minus NA square. So N2 is equals to root of N1 square minus NA square. So like this we get the expression of N2, refractive index of cladding. So let's substitute the values. N2 is equals to root of N1 is 1.45 whole square minus NA is 0.16 whole square. So calculating, we'll get 1.44 is the cladding refractive index. Next, the refractive indices of core and cladding materials of a step index optical fiber are 1.48 and 1.45 respectively. Simulate numerical aperture and acceptance angle. So the given data, refractive index of core and cladding, that is 1.48 and 1.45. So that is refractive index of core is N1 1.48, refractive index of cladding 1.45. So calculate the numerical aperture and the acceptance angle I maximum. So formula which we use here is NA. So to find numerical aperture, it is equals to root of N1 square minus N2 square. So root of 1.48 whole square minus 1.45 whole square. So it is equals to 0.2965. This is the numerical aperture. And for acceptance angle, I maximum is equals to sine inverse of NA. So sine inverse of 0.2965. So the value becomes 17 degrees 15 minutes. This is the acceptance angle. Acceptance angle is nothing but acceptance angle is nothing but the maximum angle made with fiber axis that enters into the core. So that is if we take the cross section of the optical fiber, so cladding, and this is the core, and this is the fiber axis. So the maximum angle made with optical fiber that enters into the core. So this is the core having refractive index N1. This is the cladding having refractive index N2. So the maximum angle that made with the maximum angle of the light ray that made with fiber axis enters into the core, that is I maximum. So this is the maximum angle of the incident ray made with fiber axis that enters into the core. So that I maximum acceptance angle, that is acceptance angle, is equals to 17 degrees 15 minutes. 17 degrees 15 minutes. With this degree of angle, that light ray enters into the core to get multiple reflections and gives the output. An optical fiber has a numerical aperture of 0.2 and a cladding refractive index of 1.59. Find the acceptance angle for the fiber in water, so which has a refractive index of 1.33. So here numerical aperture is equals to 0.2, N1 is equals to cladding refractive index. So cladding refractive index mentioned with N2, N2 is equals to 1.59. And we need to calculate the acceptance angle. So acceptance angle I maximum. So we need to calculate I maximum, which is at water. In water we have to calculate. So N naught. So the refractive index of water is N naught. So that N naught is equals to 1.33. So the formula we use here, numerical aperture, it is equals to root of N1 square minus N2 square by N naught, which is in the refractive index of the medium. So that is equals to numerical aperture 0.2 divided by 1.33, where numerical aperture is equals to, normal case, numerical aperture is equals to root of N1 square minus N2 square. So that is equals to 0.2. So here substituting 0.2 divided by N naught, so that is equals to 1.3. So sine inverse of NA, that is numerical aperture is equals to 0.2 divided by 1.33. So for getting acceptance angle, I maximum is equals to sine inverse of 0.2 divided by 1.3. So it is equals to sine inverse of 0.1504. So we'll get 8.6 degrees. This is the maximum acceptance angle. So then the next problem, calculate the fractional index change. So delta we have to calculate. So calculate the fractional refractive index change for a given optical fiber if refractive indices of core and the cladding are 1.563 and 1.498 respectively. So the refractive index of core is 1.563 and the cladding refractive index is 1.498. So we need to calculate the fractional index change. So the fractional index change delta is equals to N1 minus N2 by N naught. So it is equals to n by. So 1.563 minus 1.498 divided by 1.563. So it is equals to 0.0416. This is the fractional index change. Then when the mean optical power launched into an 8 kilometer length of fiber is 120 microwatts. The mean optical power at the fiber output is 3 microwatts. Find overall signal attenuation and the signal attenuation per kilometer. So in this problem, the given data is length of the optical fiber, that is 8 kilometers, and the input power is 120 microwatts, and then output power is 3 microwatts. So we need to calculate the overall signal attenuation and also signal attenuation per kilometer. So overall signal attenuation or loss in decibels through the fiber is alpha decibels L is equals to 10 log pi power input by power output base 10. So let's substitute 10 log of power input is 120, micro is 120 into 10 power minus 6 watts divided by 120 into 10 power, our output is 3 microwatts. So it is equals to 3 into 10 power minus 6 watts. So 3 into 10 power minus 6 base 10. So 10 log of 40 base 10. So the signal attenuation is equals to 16 decibels. And the signal attenuation per kilometer for the optical fiber is alpha decibels L is equals to 16 dB. So L is length, so that is 8 kilometers. So that alpha decibels is equals to 16 by L decibels per kilometer. So L is 8. So decibels per kilometer. So it is 2 decibels per kilometer. So this is the signal attenuation per kilometer. So the references are Engineering Physics by K. Tyagarajan, Aeronautical Education Private Limited, New Delhi, and a textbook of Engineering Physics by M.N. Avadanulu, Physics Sagar, S. Chand and Company, New Delhi. Engineering Physics by Dr. M.R. Mughal, Anuradha Publications, Chennai, 6,70,000. And then Engineering Physics by P.K. Palaniswamy, 4th edition, Scientific Publications, Private Limited, 6,70,000. These are the references books which belongs to this topic. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.